Introduction to the Electromagnetic Brain. The purpose of this video is to transform the issue of consciousness in neuroscience into an electromagnetic problem. In today's world, it is widely accepted that the brain is an electromagnetic source. Now, in this series of videos, I intend to show where this idea comes and why there is a field called neuroelectromagnetics. Many of you may be familiar with the two devices, EEG and MEG. In other words, if we place sensors on the head, they record signals. The presence of these signals proves to us that a series of electromagnetic activities are taking place inside the brain. The connection between the brain and electromagnetism. This slide illustrates these sensors and the recorded signals. EEG sensors can measure the brain's electrical fields, while MEG sensors detect the presence of magnetic fields. As the results from these signals show, our brain has electrical and magnetic signals that vary over time and can be recorded from all areas of the brain. The primary goal of neuroelectromagnetics is to relate the temporal and spatial aspects of these signals to the neurophysiological realities of the brain, or the functioning of neurons. This understanding can have numerous applications. Brain disorders such as epilepsy, Alzheimer's, or Parkinson's can be diagnosed and monitored by creating functional images of the brain, and if surgery is necessary, the relevant information about the surgical site can be obtained. Human head anatomy. Now let's see where these signals originate from. To understand this, we first need to take a look at the human head and the position and structure of the brain within it. A general schematic of the human head is shown here. As you can see, the human brain is well protected inside the skull, which is a hard, bony structure. Additionally, layers of the scalp, composed of fat, muscle, skin, and hair, provide further protection for the skull. Beneath the skull, there is a dual-layer protective membrane called the dura, which encloses a fluid called cerebrospinal fluid, CSF. Within this space, there is also a double-layered arachnoid tissue and veins responsible for returning blood from the brain. The final layer is the pia mater, which covers the surface of the brain. Beyond these protective layers, we reach the brain tissue itself, which is broadly divided into two parts, the gray matter and the white matter. Let's focus on the brain tissue. This tissue includes parts such as the cerebral cortex, white matter, cerebellum, as well as the limbic system, midbrain, brainstem, and cerebellum. The cerebral cortex, which is the gray matter of the brain, is composed of two main hemispheres that are connected by axonal fibers called the corpus callosum. Additionally, the cerebral cortex can be categorized based on functional or structural classifications, and generally, it has topological divisions, such as its division into four lobes: occipital, temporal, parietal, and frontal, which are shown in the figure. Functionally, the occipital lobe is associated with regions in the cortex responsible for processing sensory information, including the primary visual cortex, related to visual information, the primary auditory cortex, related to auditory information, and the primary somatosensory cortex, related to bodily sensations. The region of the cortex involved in motor control is the primary motor cortex, and other areas of the cortex are associated with learning, perception, memory, planning, and movement. The cerebral cortex itself is composed of several different parts, each responsible for a specific function. Figure 5.8 shows these parts along with their functional roles. The figure shows the various regions of the cortex and the division of the brain into functional sections. In a lateral view, the two hemispheres within the brain are responsible for different functions. The left hemisphere is involved in the analysis of information and the control of sequential events, e.g., speaking, understanding the pace of others, reading, and writing. It handles part of the problem, while the right hemisphere is responsible for synthesis, combining separate elements to create a bigger picture, such as drawing a plan or reading a map. It is also involved in understanding the meanings of statements, and damage to this hemisphere can alter this ability. Although they are responsible for different tasks, these hemispheres exchange information through a bundle of connecting axons known as the corpus callosum. Behind the central sulcus are lobes responsible for learning, perceiving, and remembering. These include the occipital lobe, which processes visual information, the superior temporal lobe, which processes auditory information, and the parietal lobe, which processes movement and sensory information. However, these lobes also perform other functions, such as processes related to perception and understanding of the body. The frontal lobe is responsible for motor movements, such as planning strategies for action. The left frontal lobe, specifically Broca's area, is involved in controlling speech expression. The limbic system, a key area in the cerebral hemisphere, is crucial when it comes to learning, memory, and emotions. It consists of various regions, including the limbic cortex, hippocampus, and amygdala, the latter two of which can be found in the temporal lobe. The amygdala is related to emotions and behaviors like aggression, while the hippocampus plays a role in learning and memory. Individuals with hippocampal damage may struggle to learn new information but can still recall and remember past memories. Sensory information is received by the hypothalamus, including details about changes in the body's physiological state, such as body temperature. The hypothalamus also manages the pituitary gland, which is connected to the lower part of the hypothalamus, and controls the endocrine system, glands. Hormones function similarly to neurotransmitters, stimulating receptors to produce effects, but they work over much greater distances. When these hormones bind to receptors, their effect leads to physiological reactions in target cells, receptors in specific cells. The hypothalamus manages homeostatic processes through control of the pituitary gland and the autonomic nervous system. However, it can lead to more complex neural circuits in the cerebral cortex, resulting in learned behavior. The final figure also shows the various regions of the brainstem. The brainstem is composed of three parts: the medulla oblongata, which is responsible for managing heart rate, blood pressure, and breathing rate, the pons, which manages sleep and waking processes, and the midbrain, which controls body movement during fight-or-flight situations and when engaging in sexual behavior. If we focus on the tissue of the cerebral cortex, geometrically, it features grooves known as sulci and ridges called gyri. The gray matter, which is at its thickest between 2 to 3 mm, consists of 6 neuronal layers. Neurons, which are the primary elements involved in the brain's conscious activities, are located in these layers. Each neuron is composed of a nucleus, dendritic branches, and an axon that connects to other neurons at the synapse. Figure in right hand shows schematic view of distribution of the cortical neurons. The cross-sectional view of the simplified head model illustrates layer 3 and 5 pyramidal neurons, PN, and basket cells. The cortex can be represented by the crown, which is the top of the gyrus, the lip and the bank along the sulcus. Note that the axons of layer 5 PN in the lip and bank bend after they cross the boundary between the gray matter and white matter. In addition, it shows schematic view of the distribution of the PN. Note that neurons have relative orientations according to their locations. Neural electrical activity is driven by the generation and propagation of action potentials, essential for communication between neurons. An action potential occurs when a neuron's membrane potential rapidly changes due to the influx of sodium ions, Na, during depolarization, followed by the efflux of potassium ions, K, during repolarization. This electrical impulse travels along the axon of the presynaptic neuron to the synapse, where it triggers the release of neurotransmitters into the synaptic cleft. These neurotransmitters bind to receptors on the postsynaptic neuron, causing ion channels to open or close, which alters the postsynaptic neuron's membrane potential. If the change is sufficient to reach a threshold, a new action potential is generated in the postsynaptic neuron. This precise electrochemical process enables the transmission of information throughout the brain, with the collective ionic currents generating electromagnetic fields that are vital to neural function. During neural activity, when a single neuron is activated, it generates an excitatory postsynaptic potential, EPSP, at a synapse, leading to local electrical currents within the neuron. These primary currents produce electromagnetic fields around the neuron. Due to the conductive properties of brain tissue, these primary fields can induce secondary currents and fields in the surrounding tissue. These secondary currents and fields can propagate beyond the immediate area, contributing to the brain's overall electrical activity. The resulting electromagnetic signals can be detected by both electroencephalography, EEG, which measures voltage changes at the scalp, and magnetoencephalography, MEG, which detects the magnetic fields generated by these currents. The detection and analysis of these signals allow for insights into brain function, which I will explain further in the next slide of the presentation. In this slide, to understand EEG and MEG foundations, we will connect our discussion to the generated leads and field patterns. As shown in the figure, when a neuron generates an action potential, the resulting electrical activity creates local fields that propagate through brain tissue. The primary current in a population of active neurons gives rise to secondary volume currents, which spread throughout the head. As the skull forms a semi-insulating barrier, the outer currents are considerably weaker. A portion of this current flow between the contact areas of two electrodes, thereby experiencing a resistance and causing the potential difference, according to Ohm's law. In addition, magnetic fields are caused by both the primary and secondary currents. They intersect the cross-sectional area of the pickup coil and contribute to the magnetic flux psi measured by MEG. Understanding the generated fields is essential for interpreting EEG and MEG signals. The patterns of electrical and magnetic fields vary based on the orientation and location of neuronal currents. EEG patterns represent the summed electrical activity on the scalp, while MEG captures magnetic field patterns resulting from neuronal currents flowing perpendicular to the scalp surface. Understanding these field patterns and their interactions between EEG and MEG measurements enhances our ability to interpret the brain's electrical and magnetic activity. Additionally, these concepts bridge the forward and inverse electromagnetic problems, which will be discussed in the next slide. The figure illustrates the structure of the neuroelectromagnetic inverse problem. Neural activity is described physiologically as originating from networks of interacting neurons or neural populations, often modeled as interconnected neural masses. These models predict the current source density, CSD, reflecting activity at a biophysical level. The CSD is then translated into measurements using a model that accounts for the head as a volume conductor and the properties of the sensors. Inverse methods aim to reverse these forward models to reconstruct the CSD or neural sources. Forward problem involves modeling how neural activity generates EEG or MEG signals. By knowing the source configuration, such as the location and orientation of neuronal currents, the forward problem predicts the expected signals at the electrodes or sensors. The central question in neuroelectromagnetics is how to solve the inverse problem. Given measurements of external fields in the brain, how can we trace back to and localize the neuronal sources that generated these fields? This will be discussed in detail in the upcoming video. The inverse problem involves determining the location and orientation of neural sources based on the measured EEG or MEG signals. This problem is more complex because different neural configurations can produce similar signals, requiring advanced algorithms to estimate the most likely sources of the observed data. In the previous video, we discussed the concept of neuroelectromagnetism and the presence of electromagnetic sources in neurons. Now, in this video, we aim to first model neurons as electromagnetic sources. In other words, we will transition from neurophysiology to the concept of an electromagnetic source that generates action potentials. Next, we will model the arrangement of neurons and their resultant fields. Finally, we will provide a brief overview of electromagnetic modeling of brain tissues by first introducing geometric information, which we will then reconstruct and transform into a material from an electromagnetic perspective. Ultimately, we will model the brain as an electromagnetic environment that includes electromagnetic sources. A source model in the context of brain electrical activity is a mathematical formulation that characterizes the primary current density generated by neural sources within the brain as a function of both space and time. The source space is defined by all parameters of a parametric source model, effectively spanning the possible configurations of the neural activity. The instantaneous primary current density, denoted as J, are wink with tongue sticking out, where R is the spatial location and P represents the parameters of the source model, can be approximated as a vector within this source space. As the neural activity evolves over time, the primary current density J, RT wink with tongue sticking out, traces a trajectory within the source space. The electromagnetic fields generated by this time-evolving current density are described by Maxwell's equations, modified for the quasistatic approximation typically used in bioelectromagnetism. These include nabla E equals ρ/epsilon, where E is the electric field, ρ is the charge density, and epsilon is the permittivity of free space. Nabla times E equals del B/del T, relating the electric field to the time variation of the magnetic field B, nabla B equals 0, indicating the absence of magnetic monopoles, and nabla times B equals mu, J plus epsilon del E/del T, where mu is the permeability of free space and J is the primary current density. These equations govern how the current density within the brain leads to the generation of electromagnetic fields, which can be measured externally by techniques such as electroencephalography, EEG, and magnetoencephalography, MEG. The source model, therefore, serves as a crucial framework for linking the dynamic internal neuronal activity to the observable electromagnetic signals, allowing for the reconstruction and interpretation of brain dynamics from external measurements. As previously mentioned, the opening and closing of sodium and calcium pumps located in the walls of the neuronal cell create a voltage difference between the intracellular and extracellular spaces. This voltage change, in turn, triggers the opening and closing of adjacent pumps, leading to the flow of current along the axon. In the simplest case, this process can be modeled as a current dipole. As shown in the top figure, a neuron can be modeled as an electric dipole, where the flow of ionic currents across the cell membrane during action potentials creates distinct regions of positive and negative charge. This dipole moment is dynamic, varying as the action potential travels along the axon. By modeling a neuron as a dipole, one can simulate the electrical field generated by neuronal activity, which is crucial for interpreting data from electroencephalography, EEG, and magnetoencephalography, MEG, which is shown the equivalent electromagnetic model in the right side of the figure. The bottom of this slide shows the configurations of neurons and major intracellular currents. In pyramidal cells, the long, thick apical dendrite creates a preferred direction for intracellular currents, making them detectable from a distance. However, detectability depends on the cell's positioning and orientation. As shown in C, many pyramidal cells in the cortex align in parallel, allowing the far fields of their currents to add up, which can be detected by EEG or MEG. Conversely, in circular alignments like in the hippocampus, D, these fields cancel out. Additionally, symmetric neurons, as shown in B, also tend to have currents that cancel out within the cell. Configurations A and C are known as open fields, while B and D are closed fields. An extended cortical activation with variable strength and orientation of the primary current density can be modeled by electric current dipoles. A single focal source model is chosen such that it optimally approximates the sum effect of all these currents, which is demonstrated by red arrow. Alternatively, the source area might be subdivided into multiple volume elements, each represented by an electric current dipole of its own, which is called distributed source model, demonstrated by blue arrows. As shown in the right side figure, 3 different source models can applied: a distributed model, left column, where the source area is uniformly divided into small elements each described by an electric current dipole; a multiple focal model comprising 2 electric current dipoles, middle column; and a single focal model comprising 1 electric current dipole, right column. In the upper row, we see a more continuous distribution with a sharper focus at the top and a broader blob at the bottom. While the single focal model is clearly inadequate, the multiple focal model accounts quite well for the true distribution, although the broader blob is less well captured. The distributed model is a more accurate description. In the lower row, the primary current density features a single focus, which is well approximated by a single focal source. The other 2 models are clearly redundant. In this slide, we are going to discuss the spatial distribution of the produced external fields and their relation by the orientation of the dipoles. As previously mentioned, based on the concept of the equivalent current dipole, the synchronized activation of one part of the cortex can be detected as the external field. These concepts are shown in the top side figures of this slide. In addition, their location, orientation, and their polarity will define the spatial distribution of external field. As shown in the bottom figures of the slide, tangential dipoles produce external magnetic field, but radial dipoles don't create magnetic fields. It means doesn't seen in MEG. To go deeper in the context of the spatial distribution of the external fields here in this slide, we are going to show the typical topographies of EEG and MEG on real head geometries caused by a single dipolar source positioned closely underneath the inner surface of the skull. Topside potential distribution of EEG and magnetic flux density distribution of MEG on the head surface for a tangential dipole. Positive potentials are drawn in red, negative ones in blue. The potential difference between the 2 contour lines is 10 microvolts. Bottom side for radial dipole. Positive flux densities, drawn in red, denote flux coming out of the head, while negative flux densities, blue, denote flux going into the head. Normally the flux difference between 2 contour lines is 1 picotesla. In the previous slide, we concentrated on the possibilities for the generation of local membrane potential changes, which was for proximal excitatory synapses. Now in this slide we are going to demonstrate the impact of the polarity of EEG and MEG. Excitatory and inhibitory synapses create positive and negative local postsynaptic potentials, respectively. Excitatory synapses can be located distal, away from the soma, or proximal, near soma, leading to currents away or towards the cortex, PL, surface, respectively. Inhibitory synapses are mostly on or near the soma, causing intracellular currents to flow away from the PL surface. Depending on the location of the active neurons on the cortex, currents flowing away from or towards the PL surface can effectively be oriented perpendicular, on the gyral crown, or tangential, on the sulcal wall, to the head surface. Typical EEG and MEG topographies for source configurations are shown in the right side column. Another parameter that should be taken in account is the impact of the rotation. First, we are going to demonstrate the decomposition of the rotated dipole in radial and tangential form. For this purpose, in right side of the slide in figure A2 dipoles are considered by location in close proximity. Distance is almost equal to 1 cm, one on the gyral crown, which is demonstrated by red arrow, the other one on the sulcal wall in green arrow. In figures C, D the simulated EEGs for these dipoles, interpolated between 124 EEG electrodes, small green disks, and viewed from above. In B the dipoles from A are shifted to a common position without changing their orientation. Hence in figures E, F the EEG topographies are virtually the same as in C and D. Thus, the differences between the two dipoles, as observable by EEG, are rooted predominantly in the difference in dipole orientation and not in dipole location. In left side of the slide, we demonstrated the cortical currents, volume currents, and scalp topography from different directions of localized dipoles. In this figure pyramidal cells and their apical dendrites are symbolized by diamonds and thick outward bars. A subset of return current loops is depicted by arrows in light red to illustrate where they create positive and light blue where they create negative voltages. As shown in figure, depending on the net orientation of the cortical patch, the zone of maximal inflow from scalp into depth shifts from above the patch in radial, to more posterior in tangential and fully posterior in oblique. These currents create the typical 3D voltage topographies on the scalp related to the cortical convexity in radial case, in the depth of a sulcus in tangential case, and the more common case of an oblique net current involving both superficial and sulcal cortex. Dynamic source modeling is a behavior modeling approach for neurons based on feedback principles. In this model, shown in the left figure, the state variable evolves according to a differential equation and an initial condition. An output equation converts the internal state, such as the mean membrane potential, into a source model parameter like dipole strength. The Hodgkin-Huxley model, one of the most popular dynamic source models, is depicted on the right. It includes voltage-gated channels for potassium and sodium, described by nonlinear differential equations, with other currents summarized by the constant leakage conductance GL. This concludes our introduction to source modeling, with more details to follow in future videos. Space modeling is a key principle for solving neuroelectromagnetic problems. To achieve this, the head must be realistically modeled as an electromagnetic space. This slide illustrates the transformation between a realistic head and a spherical volume conductor model based on boundary value modeling. The simplest model is represented by concentric spheres, which are shown in red with fixed ratios between the radii, corresponding to the scalp, outer skull, and inner skull surfaces. Alternatively, the head can be modeled using concentric ellipsoids, which are piecewise homogeneous and isotropic or radial/tangential anisotropic. These are fitted to the upper part of the tessellated scalp surface, which are shown in green contour extracted from MRI data. To map a point from the real head volume to the spherical model volume or vice versa, a beam from the origin through the original point, characterized by the spherical angles theta and alpha, is considered, and the intersection ratios with the respective head surfaces are computed. This method allows for the transformation of both source and electrode positions, with electrode positions corresponding to an orthogonal projection onto the surface of the fitted sphere. The field approximation and mathematical treatment for these models is achieved through a quasi-analytic solution using spherical harmonic expansion of the electric potential. Each material in the electromagnetic model is characterized by its permittivity, permeability, and conductivity. The table provides details on the domains, their boundaries, and the corresponding electric and magnetic properties. To develop an accurate volume conductor model, the boundary element method, BEM, is a widely used approach. As illustrated in the slide, the process begins by loading and reading anatomical data, such as MRI scans. The MRI images are then resliced to ensure that the voxels are isotropic, meaning they have the same dimensions in all directions. This reslicing step is crucial for simplifying the subsequent segmentation process. Next, the MRI data is segmented to differentiate various compartments, including the scalp, skull, and brain. Following segmentation, a triangulated surface mesh is created for the BEM. This method involves defining several boundaries for each tissue type, such as the scalp, outer and inner skull surfaces, cerebrospinal fluid, CSF, and brain tissues, including both gray and white matter. The triangulated surfaces effectively describe these boundaries, and each compartment is treated as homogeneous and isotropic. The finite element method, FEM, is a crucial technique for creating electromagnetic space models of the human head, particularly for neuroelectromagnetic source reconstruction problems. Similar to the boundary element method, we start by acquiring and pre-processing anatomical data, such as MRI or CT scans, followed by the segmentation of different tissues. Next, we generate a finite element mesh, either tetrahedral or hexahedral, that balances detail with computational efficiency. This slide presents two FEM models of the human head with multiple tissue segmentations and varying levels of detail, emphasizing the role of different mesh types in accurately representing anatomical structures. In FEM, accurately assigning material electromagnetic properties and defining boundary conditions are essential. This concludes our presentation. In the next video, we'll delve into the application of FEM in solving forward problems and explore the specific uses of various mesh types. Now that we have introduced the brain as an electromagnetic space and neurons as electromagnetic sources, let's delve into the topic of Neuro-Electromagnetic Forward Problem, focusing on how electromagnetic fields are represented as a result of neuronal activities. In this video, we will explore the direct solution of the Neuro-Electromagnetic Forward Problem by building on concepts such as neuronal sources and electromagnetic space, which were covered in previous videos. We will start by discussing the head model, the source model, and the sensor model. Next, we will explain the formulation of the Neuro-Electromagnetic Forward Problem and its different solutions. Finally, we will examine the electromagnetic solver used to extract lead fields. In this slide, we outline the information flow and fundamental components of the forward Neuro-Electromagnetic Problem. The process begins by incorporating anatomical and spatial data related to head and source models, as well as information on the positions of electrodes, achieved through electrode position registration. Next, we formulate the forward problem by defining the electromagnetic solvers, which address the impedance inversion problem to estimate volumetric currents and surface potentials. These are then represented in the lead field matrix playing the role of the impedance, which serves as the foundation for mapping neural activity to measurable signals. Let's begin with head modeling. This model incorporates three types of information: geometrical, anatomical, and electrical features. To extract the geometrical information, we first create a 3D model of the individual using MRI images, and then reconstruct the geometrical data. To align this data with the realistic anatomy of the head, segmentation is applied, which separates relevant segments of human head tissue such as the scalp, skull, and the white and gray matter of the brain. In the next step, each segment is meshed. The results of this step are shown in the slide using field trip software. The third type of information that needs to be incorporated into the head model is the electrical features. At neural activity frequencies, the head model is considered a volume conductor, allowing currents generated by the brain to propagate through the head. For electrical modeling at low frequencies, a crucial parameter for the forward model is the conductivity of the head tissues. There are several challenges in determining conductivity, such as the significant variability in tissue conductivities among individuals, which makes the conductivity values often inaccurate and not individualized. For white matter, anisotropy can be deduced using individual diffusion tensor imaging, DTI, and skull anisotropy can be calibrated individually. Generally, standard isotropic constant values are used. The table in this slide shows the relevant electrical features for different head tissues at 50 Hz. After creating the head model, where geometrical, anatomical, and electrical features are integrated, the next step is developing the source model, with source locations constrained to the gray matter compartment. This localization is linked to the segmentation process, which includes creating the triangular surface meshes and hexahedral volumetric meshes, allowing for precise source localization within the gray matter based on mesh nodes. Since the sources are placed in the gray matter, the accuracy of the source model is directly dependent on the accuracy of the head model. As mentioned in the previous video, a dipole current source is often an appropriate choice for the source model. For this, a list of 3D positions and orientations must be defined and incorporated into the head model. This slide presents the meshes and localized sources within the gray matter, as extracted from the field trip software results. The final step in the modeling process before solving the forward problem is sensor localization, which ensures that EEG and MEG measurements accurately reflect the underlying neural activity. On the right side of the slide, we show typical sensor arrangements for EEG, using the 10-20 or 10-10 system on the scalp, and for MEG, using a helmet-like device that captures magnetic fields without direct contact. Both arrangements are essential for precise data interpretation. We also demonstrate how field trip software is used for coordinate matching and sensor localization, aligning sensor positions with the head model to ensure accurate data representation. In this slide, we outline the forward model for EEG based on Maxwell's equations. As you can see from the formula in left hand, the electric field E is the negative gradient of the electric potential V, expressed as E equals nabla V. In the absence of currents, the potential satisfies Laplace's equation, nabla superscript 2V equals 0. When considering conductivity sigma, the equation adjusts to nabla superscript 2V equals sigma slash epsilon asterisk j, where epsilon backslash epsilon is the permittivity and jjj is the current density. The passive volume current induced by the conductivity is given by J underscore V equals sigma E. Therefore, the forward model for EEG is described by the equation nabla, sigma nabla V equals J, which details how the electric potential VVV is influenced by conductivity and current sources. For the magnetic field, as you can see in the right side formulation, we use Maxwell's equations where the curl of the magnetic field B is equal to the permeability μ0 times the current density J, and the divergence of B is 0. From this, we derive the magnetic vector potential A using the Coulomb gauge, leading to Poisson's equation for A, nabla superscript 2A equals μJ. The solution is given by A equals mu integral J slash R dV, and the magnetic field B is computed using the Biot-Savart law, B equals mu slash 4 pi integral J times R forward slash R superscript 3 dV. Combining this with the EEG forward model, the forward model for the magnetic field is expressed as B equals mu slash 4 pi integral J sigma nabla V times R forward slash R superscript 3 dV. To solve the forward problem in EEG and MEG, which involve partial differential equations, PDEs, for electric and magnetic fields, numerical methods are employed. The process begins by translating these PDEs into linear matrix equations, as illustrated in the schematic on the left side. Numerical techniques such as the finite element method, FEM, and boundary element method, BEM, are used for this conversion. Both methods involve discretizing the head model into a mesh. In FEM, the head model is divided into small volume elements, and the PDEs are reformulated into a weak form suitable for numerical solution. This involves integrating the PDEs over each element to account for field variations, creating local stiffness matrices. These local matrices are assembled into a global matrix, which incorporates boundary conditions and source terms, such as currents. The global matrix equation is then solved using numerical linear algebra techniques to determine the electric potential or magnetic vector potential at each node in the mesh. In BEM, only the surface of the head model is discretized into boundary elements. The PDEs are converted into boundary integral equations, which simplifies the problem to a surface-based system. These integral equations are used to create a matrix system, which is then solved to obtain the potential on the surface. From this surface potential, internal fields can be computed. Both methods result in vectors of values representing potentials at the nodes or surface elements, which are then used to compute the electric and magnetic fields. The schematic shows the meshing process for both BEM and FEM, highlighting the discretization approach used in each method. To solve the coupled EEG and MEG forward problem by 3D FEM, after creating the fully meshed model of the problem space and sources as shown in this slide, we prepared a linear matrix equation to determine the electric and magnetic potential in each node of the mesh. The 3D finite element method, FEM, formulation for solving the coupled EEG and MEG forward problem is also demonstrated here. The presented formula shows the full system of equations in 3D with node indices I, J, and K for X, Y, and Z directions. The details of the matrices and vectors involved in this formulation are as follows. The matrices KV and KA are constructed from the mesh elements and consider the physical properties of the medium, such as conductivity and magnetic permeability. This system is typically solved using numerical methods such as iterative solvers. The result will give you the distribution of the electric potential V and the magnetic vector potential A across the nodes of the 3D domain, which can then be used to compute the EEG and MEG signals. Is the stiffness matrix for the electric potential, involving contributions from neighboring nodes in the mesh. It is derived from the weak form of the Poisson equation. This matrix at node accounts for the contributions of neighboring nodes in the mesh. It is derived from the weak form of the Poisson equation, where sigma is the electrical conductivity of the medium, and are the shape functions associated with nodes, and its neighboring nodes, respectively, and omega is the element domain. In other words, this matrix relates the potential at node to the potentials at neighboring nodes. Is the stiffness matrix for the magnetic vector potential, involving contributions from neighboring nodes. This matrix is derived from the weak form of the vector potential equation, where mu is the magnetic permeability of the medium, Nijk and Nijk are the vector shape functions associated with nodes, Ijk, and its neighboring nodes, ijk. Nabla times nijk represents the curl of the vector shape functions and omega e is the element domain. This matrix governs the relationship between the magnetic vector potential aijk at node, ijk, and the vector potentials at neighboring nodes. AN are the coupling matrices that link the electric potential and the magnetic vector potential. And represent source vectors at node. The source vectors represent the contributions of primary currents and external sources at node. IJKFV is the source vector related to the electric potential V and FA is the source vector related to the magnetic vector potential A. To visualize the results of solving the forward problem in EEG, the sensor space activation pattern displays the distribution of electrical activity across the scalp, reflecting the combined effects of neural sources. On the left side of the slide, the topography of activation patterns is shown as power modulation across 3 frequency bands over time intervals, normalized for comparison. On the right side, the principle of the lead field matrix is illustrated, offering another method of visualizing analysis results. As shown on the top right side, the outputs of the sensors, here EEG electrodes, at different points in time, here spaced by 1 millisecond, are arranged in the measurement matrix. Each entry of the lead field matrix contains the output of one sensor due to a unit dipole at a particular position and with a particular orientation, here x, y, z. The matrix of the dipole magnitudes contains the strength for all dipoles at all time steps. The scalar product of one row of the lead field matrix with one column of the dipole magnitude matrix yields the output of the respective sensor at the respective time point. At the bottom, the lead fields in the XYZ directions for an example of superficial source is demonstrated. The term lead field derives from an alternative term for an EEG electrode pair, lead. If a current of unit strength is injected into a lead, the lead field is defined as proportional to the current density that would occur throughout the head. According to the reciprocity theorem, this is equivalent to the sensitivity profile of the lead, which is approximated by a rho in our lead field matrix. The forward model can be used in inverse procedures in the form of a nonlinear function that needs to be re-evaluated for each new source parameter vector. This can be computationally rather costly. However, in several scenarios, for example, when using minimum norm or scanning, we can make use of a precomputed lead field matrix, also called influence or gain matrix. This concept exploits 2 major properties of the forward solution. First, part of the source parameters, particularly the dipole strength, exercise a linear, scaling, influence onto the measurements. Second, the influences of multiple sources, e.g., dipoles, can be superimposed linearly. To demonstrate the importance of the leads filed here, the magnitude and orientations of the lead fields for head model for a superficial source is demonstrated. The magnitude of lead fields quantifies how strongly these neural sources influence each sensor, indicating the strength of the field at each electrode. In contrast, the orientation of lead fields describes the direction in which the neural activity is projected onto the sensors. The vectors plots show they are normal to the scalp surface. Comparing the activation pattern with the magnitude and orientation of lead fields helps to understand how well the observed scalp potentials map to the underlying brain sources and their spatial configuration. As discussed in the Electromagnetic Brain video series, current research in neuroelectromagnetics is primarily focused on source reconstruction from EEG and MEG signals. In separate videos, we provided an overview of direct and inverse problem-solving methods for reconstructing these sources. If you haven't watched those videos, I recommend starting with the Electromagnetic Brain playlist before proceeding with this series. In this new series, we will explore the challenges and limitations of reconstructing neuronal sources from EEG and MEG signals, followed by an in-depth examination of advanced methods in neuroelectromagnetics. In the next video, we will take a closer look at problem space modeling, covering it in more detail. Following that, we will delve into source modeling, discussing it comprehensively and introducing relevant research papers in the field. Additionally, we will introduce and thoroughly examine the full-wave solution approach to solving the neuro-electromagnetic problem across the entire brain, using the corticothalamic system as an example. Finally, we will explore the concept of endogenous brain electromagnetic fields. Throughout these videos, we will address the key weaknesses in modeling and solving direct problems, categorizing them into 3 main areas: problem space modeling, source modeling, and electromagnetic solvers. To illustrate this, the basic models will be shown on the left side of the slide, while the advanced techniques will be introduced on the right. As we discussed in previous videos, modeling the problem space begins with segmenting MRI images and creating a mesh from these segments. These models, as depicted on this slide, typically start with a basic representation of the main tissues, such as the scalp, skull, and brain. However, it's important to note that these basic models significantly differ from the actual anatomy of the human head. On the left side of the slide, you can see these foundational models, while on the right side, more advanced models, introduced in recent studies, are presented. These advanced models take into account complexities such as the heterogeneity of the skull and white matter, the impact of flow of cerebrospinal fluid, CSF, the cerebrovascular effects, and even the intricate structures on the cortex with varying thicknesses, which also consider different arrangements of neuronal layers. Incorporating these factors allows for the creation of a more sophisticated model that more accurately represents the neural-electromagnetic source reconstruction space. These advanced modeling techniques will be discussed in detail in the upcoming videos. Let's delve into the differences between actual neural models and those used in research. Traditionally, neurons are modeled as equivalent current dipoles, a simplification that serves well for many applications. However, when we require more precision, especially in understanding individual neuron dynamics, we turn to advanced models like the Hodgkin-Huxley model, which simulates the ionic currents and action potential generation in detail. On a larger scale, we use the neural mass model, NMM, which captures the collective behavior of neuron populations. This model is particularly useful for simulating brain activity as observed in EEG or MEG signals, focusing on the overall synaptic interactions and how different neural populations communicate. In cutting-edge research, we also encounter the neural nanometric model, which pushes the boundaries by modeling neurons at the molecular level. Here, each sodium-potassium pump, crucial for maintaining the neuron's electrochemical gradient, is not treated as a single unit but rather as a collection of multiple sources. This allows for an intricate understanding of the ionic exchanges and molecular processes that govern neuronal function. This level of detail is invaluable for exploring new frontiers in neuromedicine, where such precise models can lead to breakthroughs in understanding and treating neurological disorders. In neuroelectromagnetics, due to the low frequencies of brain signals, the static forms of Maxwell's equations are typically used, specifically electrostatic and magnetostatic models. These models involve solving the Poisson equations derived from Maxwell's equations under static conditions, usually employing methods such as the finite element method, FEM, or boundary value problem, BVP, approaches, which have been discussed in previous videos. A simplified version of these assumptions is shown on the left side of the slide. However, recent research has proposed significant improvements to this approach. One such method involves solving the full-wave Maxwell's equations for neuronal sources using the 3D finite difference time domain, FDTD, method. Initially, a full-wave electromagnetic model is applied at high frequencies, and then high-to-low frequency converters are used to adapt the electrical parameters of the problem space, such as tissue conductivity, to lower frequencies. This allows for an estimation of the neuronal field distribution within the brain. On this slide, images of the proposed models are displayed, and these topics will be discussed in detail in the video dedicated to the mathematical framework of neuroelectromagnetics in this playlist. In this slide, we transition from computational methods used to extract neuronal sources to exploring how these findings contribute to modeling consciousness through electromagnetic fields. The electromagnetic brain concept, which has gained recent attention, suggests that consciousness is linked to endogenous electromagnetic fields generated by neuronal activity. Studies, such as Galinsky's, demonstrate the presence of waves in the cortex that play a key role in these fields, with corticothalamic pathways and deep brain neurons, particularly in the thalamus, being central to this process. Building on this, an inhomogeneous anisotropic model of the brain cortex predicts the emergence of weakly damped wave-like modes in the cortical layers. These modes, which challenge traditional views of signal propagation, have been confirmed through numerical simulations, showing prolonged activity that doesn't correlate with neural fiber directions. This aligns with experimental studies revealing electrostatic field activity in the form of traveling waves, sometimes observed even without direct neuronal connections. Furthermore, nonlinear coupling between multiple wave modes can produce both high-frequency spiking activity and low-frequency rhythms, offering new insights into the dynamics of brain waves. These findings have significant implications for neuroimaging techniques like EEG and MEG, which detect electromagnetic activity and contribute to our understanding of memory and consciousness. In parallel, electromagnetic field (EMF) theories suggest that consciousness arises from dynamic electromagnetic fields generated by neuronal currents. These fields form a three-dimensional energy cloud around the brain, detectable as complex EEG and MEG patterns. Recent advances in nonlinear dynamic analysis of EEGs allow us to visualize these patterns in 3D, correlating them with levels of consciousness in humans and animals. While these findings support EMF theories, they represent only a fraction of the complexity and power of our brain's electromagnetic activity. To conclude, it's important to highlight a compelling theory regarding the origins of the brain's endogenous electromagnetic (EM) field and its potential role in consciousness, as explored by Hales, 2014. This work addresses the long-standing challenge of linking EM phenomena to consciousness by proposing a biophysically realistic mechanism. It suggests that the coherent action of transmembrane ion channel currents, which generate electric and magnetic fields, may be the primary source of the brain's EM field. These ion channels function like tiny current filaments, creating structured, focused fields that can influence nearby neurons, akin to a sweeping lighthouse beam. This mechanism not only provides insight into the origins of EEG and MEG signals but also suggests a new way to understand the subjective nature of perception. By positing a decomposition of the EM field that reveals both objective and subjective perspectives, Hales offers a physically plausible explanation for how these fields might give rise to the experience of consciousness, addressing some aspects of the hard problem of consciousness. In the previous video, we explored the Neuro-Electromagnetic Forward Problem. In this video, we will delve into the Neuro-Electromagnetic Inverse Problem, also known as Neuro-Electromagnetic Source Reconstruction. We will take a closer look at the general concept of inverse problems, with a specific focus on the electromagnetic inverse problem. Following this, we will define the Neuro-Electromagnetic Inverse Problem and discuss the regularization-based solutions for addressing the nonlinear, ill-posed nature of these problems. The primary objective here is to reconstruct the neural sources responsible for the signals recorded by EEG or MEG. These signals, measured by the electrodes, will be traced back to determine which neural activations led to the observed data. Since neuroelectromagnetic source reconstruction is an inverse problem, we will begin our presentation with an introduction to the anatomy of inverse problems. Inverse problems involve the challenge of determining unknown causes from observed consequences, using predictive models, referred to as forward models, that link causes to consequences in a causal sequence. Forward models are typically well-posed, meaning that causes determine consequences uniquely and stably. In contrast, inverse problems are usually ill-posed, meaning the data may be insufficient to unambiguously identify the cause, an exact solution might not exist, and much like solving a mystery, discovering the cause without additional information is highly sensitive to measurement noise and modeling errors. On the left side of this slide, we depict both conventional and advanced inverse problems, highlighting the role of estimation theory in incorporating extra information. Generally, the Bayesian methodology provides a versatile and natural way of incorporating extra information to supplement the noisy data by modeling the unknown as a random variable to highlight the uncertainty about its value. Presenting the solution in the form of a posterior distribution provides a wide range of possibilities to compute useful estimates. Inverse problems are traditionally approached from the point of view of regularization, a process whereby the ill-posed problem is replaced by a nearby well-posed one. While many of the regularization techniques can be reinterpreted in the Bayesian framework through prior design, the Bayesian formalism provides new techniques to enrich the paradigm of traditional inverse problems. Inaccuracies and inadequacies of the forward model are naturally handled in the statistical framework. Similarly, qualitative information about the solution may be reformulated in the form of priors with unknown parameters that can be successfully handled in the hierarchical Bayesian context. Additionally, we illustrate the criteria for well-posed and ill-posed inverse problems. A well-posed, stable problem is characterized by the fact that a small perturbation in the data results in only a small change in the scattering parameter upon inversion. However, if any of Hadamard's three conditions are violated, the problem is deemed ill-posed. In the middle row on the right side, a schematic illustrates how violating Hadamard's conditions leads to ill-posedness. For instance, a perturbation in the data can result in a non-unique reconstruction. An unstable reconstruction occurs when the parameters differ significantly, even when the differences in the data are small. Non-existence is a situation where the reconstructed parameters fall outside the range of physically acceptable values. At the bottom, there is also a schematic illustration showing how incorporating prior knowledge stabilizes the inversion of data. After introducing the inverse problem and discussing the characteristics of the operators involved, we will now shift our focus to inverse electromagnetic problems. In electromagnetic imaging, particularly for brain imaging, the problem is often approached as a combination of source and scattering problems. Electromagnetic brain imaging devices use multiple antennas to transmit and receive high-frequency electromagnetic waves into the brain, which interact with brain tissues, and the scattered field will be received in antenna. These interactions cause scattering due to differences in the tissue's electromagnetic properties. In scattering theory, the problem is described by the Lippmann-Schwinger integral equation, which relates the total field to the incident and scattered fields. The scattered field is expressed as the integral of the source, Green's function, and contrast function, which forms our forward model. To solve this problem, we employ an iterative method that utilizes the Born approximation at each step. During the kth iteration of this method, the total field ATOC-1 is computed for the contrast function K-1 obtained in the previous iteration, using the state equation. By substituting ATOC-1 into the data equation and applying the Tikhonov regularization method, the optimization problem is solved to obtain K. For the first iteration, K0 is chosen arbitrarily. The slide presents the formulation associated with this solution, including the closed-form solution. Additionally, a simpler qualitative approach, known as source imaging, can be used to solve the inverse scattering problem. In this approach, each scatterer within the brain is treated as an electromagnetic point source emitting high-frequency signals. The bottom of the slide illustrates this simplification, showing the confocal or backpropagation approach used to demonstrate the scatterers. The formula is applied to the set of measured difference field data ES to retrieve a qualitative indicator function Q, which provides an initial estimation of the location and size of the detected scatterers inside the head. In conclusion, neuroelectromagnetic source reconstruction, which conceptually resembles qualitative methods, focuses on identifying internal sources within the brain at lower frequencies or in the electromagnetic spectrum. In the context of the inverse neuroelectromagnetic problem, the core challenge is to estimate the brain's neural sources, e.g., current dipoles, that produce the observed signals in EEG or MEG data. Mathematically, the problem is typically framed as y equals L dot theta plus epsilon, where y represents the observed EEG MEG data, measurements at the sensors, L is the lead field matrix, or forward model, that describes how each potential source contributes to the signal observed at each sensor, theta is the source configuration vector representing the strengths and orientations of the sources, and epsilon is the noise or error term accounting for measurement noise and modeling inaccuracies. The inverse neuroelectromagnetic problem involves solving for theta, given y and L. This is challenging because L is typically ill-conditioned, leading to multiple possible solutions for theta. Due to the ill-conditioned nature of L, there are generally multiple possible solutions for theta. This makes the problem ill-posed, meaning small errors in y or L can lead to large errors in the estimate of theta. To overcome the ill-posedness, regularization techniques or constraints are often applied. In this point of view, methods to solve the inverse neuroelectromagnetic problem can generally be categorized into dipole models and distributed models based on how they conceptualize the neural sources, as illustrated in the schematic. Dipole model-based methods assume that the brain's neural activity can be represented by a small number of discrete dipoles, each with a specific location, orientation, and strength. In contrast, distributed model-based methods assume that neural activity is spread out across a large region of the brain, with the goal of estimating the continuous distribution of sources. Various methods, including Bayesian analysis, ECD, MNE, and beamforming, offer different ways to solve theta, each with unique strengths suited to different scenarios. The choice of method in practice depends on the nature of the data, the assumptions about the sources, and the desired properties of the solution. Each method may yield different estimates of the neural sources, so selecting the appropriate approach is crucial and often informed by the specific research or clinical context. Classic dipole models like ECD and music are designed for scenarios involving a small number of discrete, well-defined neural sources, while distributed models like MNE and beamforming focus on continuous source distributions. On the right side of the slide, we present 4 of the most common methods. The Bayesian approach solves the posterior distribution by combining prior knowledge with the likelihood of the observed data, typically maximizing the posterior, map estimation, to provide a refined estimate of the source parameters. The equivalent current dipole, ECD, method assumes a small number of dipoles and fits them to the data by minimizing the error between the measured and simulated signals, using nonlinear optimization to find the best-fitting dipole parameters, location, orientation, and strength. Minimum norm estimation, MNE, minimizes the L2 norm, total power, of the source distribution, often with regularization to handle noise, providing an estimate that balances fitting the data while keeping the source configuration simple, minimizing overall strength. Beamforming constructs spatial filters to estimate the source activity at specific locations, optimizing for a directional response, with the solution being a set of filters that, when applied to the data, highlight activity in specific brain regions while suppressing interference from others. The ECD method is a powerful tool for localizing neural sources in the brain, especially in cases where the activity is believed to be focal and can be modeled with a few dipoles. The core idea behind the ECD method is to model the brain's neural activity as one or more equivalent current dipoles. Each dipole represents a small, localized region of the brain where electrical activity is assumed to originate. The ECD method assumes that the brain's neural activity can be effectively represented by a small number of current dipoles, each characterized by its location, orientation, and strength. Each dipole is a point source of current that can generate an electromagnetic field, which can be detected by EEG or MEG sensors. As illustrated in this slide, the ECD method typically employs nonlinear optimization techniques to find the best-fitting dipole parameters by minimizing the difference between the observed sensor data and the data predicted by the dipole model, which include the dipole's location, orientation, and strength. The ECD method is particularly effective when the neural activity is assumed to originate from a small number of well-localized sources, such as in the case of evoked potentials or responses to specific stimuli. However, the solution can be highly sensitive to noise and the initial guess for the dipole configuration. So here is the point to introduce the inverse neuroelectromagnetic problem, also known as inverse source reconstruction. The objective in inverse source reconstruction is to estimate the location and magnitude of neuronal sources inside the brain using EEG/MEG data. To address this, we use the EEG measured data to find the source parameters in an iterative method. In left side we brought the schematic of the iterative method based on initial assumption in fine model and updating coarse model. First, we define an initial model as a guess and solve the forward problem, which involves simulating EEG signals based on assumed neuronal sources, location and strength. Then, we define the inverse problem, which involves adjusting the source parameters to minimize the difference between the simulated and actual EEG signals. To reduce this error, we must solve the optimization problem. By using Bayesian analysis, we refine the source estimates, where according to Bayesian analysis, prior knowledge combined with maximum likelihood gives us the posterior probability. In Bayesian analysis, the initial assumptions or prior knowledge pertain to the possible locations and strengths of neuronal sources, which could be based on anatomical data, previous studies, or reasonable guesses. Using this prior information, we simulate EEG/MEG signals by solving the forward problem, which predicts what the EEG/MEG data would look like given certain source parameters. Likelihood estimation plays a key role in comparing the simulated EEG signals with the actual recorded EEG data, as the likelihood function measures how likely the observed data is given the assumed source parameters. Posterior calculation is then performed by combining the prior information with the likelihood of the observed data, which results in the posterior probability. This posterior represents the updated belief about the source parameters after considering the actual data. The optimization process involves iterating to find the source parameters that maximize the posterior probability, providing the most probable estimate of the neuronal sources based on the observed EEG data. The final output is a refined estimate of the source locations and strengths that best explain the observed EEG signals, considering both the prior knowledge and the actual data. The formulation and parameters of the Bayesian analysis are demonstrated on the right side of the slide. In this slide, we will demonstrate the process of source reconstruction using a simple model. The first step in Bayesian analysis is to derive the event model from the prior probability and maximum likelihood. To illustrate this, we use a model with a parameter theta, which has a constant and bounded prior probability that varies from min to max. In this scenario, the forward model is straightforward, where the data y are direct observations of the parameter theta. The noise on the data is typically Gaussian, with a standard deviation sigma, which shapes the maximum likelihood as a Gaussian distribution. We then calculate the event model by integrating the maximum likelihood over the range from min to max and multiplying it by the prior probability's magnitude. This model shows how the overlap between the maximum likelihood and the prior probability affects the event model, with the highest overlap occurring when the expected values of the prior and the maximum likelihood are equal. The event model decreases as the prior probability's width increases, indicating that less informative priors lead to a reduction in the event model. To further illustrate, consider a simple example where y represents EEG signals from a single electrode, which must be explained by a model involving two dipoles with known positions and orientations but unknown magnitudes. The unknown parameters are represented by the vector theta, and the forward solution is given by y equals Ly. If the noise in the signals is Gaussian, prior knowledge about the source magnitudes can be described by a bivariate Gaussian distribution. There are two key scenarios in event model formulation. First, when the response is fully known in advance, the event model equals the prior expected value probability. Second, when nothing is known, the event model is 0 for any data value. The same logic applies to posterior probability. It is a Dirac distribution when the response is fully known, or 0 everywhere when nothing is known. Finally, we will look at the graphs of prior knowledge, maximum likelihood, and the posterior probability model to understand how we determine the magnitude of the neuronal activity parameter. The minimum norm estimation method is designed to estimate distributed sources of neural activity across the brain, assuming that neural activity is spread out rather than localized to a few discrete points. MNE is useful for identifying distributed neural activity, such as in studies of sensory processing, attention, or resting state brain activity. It is particularly well suited for situations where the brain activity is expected to be spread across multiple regions. The goal is to estimate a continuous distribution of current sources across the cortical surface. MNE seeks the source distribution that minimizes the data term, which is the sum of squared residual and model term, which consider as penalty term of the source configuration. This corresponds to finding the solution with the smallest overall current strength that still fits the observed data. The minimization of the norm is often subject to regularization, which helps handle the ill-posed nature of the inverse problem by imposing additional constraints. The schematic of this constraints, which is the connection between data and model terms and objective function, is illustrated in this slide. Regularization techniques, such as Tikhonov regularization, are commonly used in MNE to prevent overfitting to noise and to stabilize the solution. The regularization parameter controls the trade-off between data fitting and solution norm, and the regularized MNE solution balances the fit to the data with the simplicity, or smoothness, of the source configuration. In addition, MNE is used widely for reconstructing neural source distributions from EEG or MEG data, aiming to find the simplest source configuration that explains the observed signals. Techniques like lasso and Loretta build on this concept to address different assumptions about brain functionality. Lasso, least absolute shrinkage selection operator, is particularly effective for identifying sparse, focal sources due to its ability to impose a strong regularization, effectively zeroing out less relevant sources. On the other hand, Loretta, low-resolution electromagnetic tomography, provides a smooth estimate of neural activity across a larger region, making it better suited for distributed sources. To illustrate the impact of choosing the appropriate method, here we brought a scenario where two distributed sources produce identical MEG signals. One is very focal, while the other is spread across many gyri and sulci. If the true activity is sparse, lasso would correctly pinpoint the focal source. If the activity is distributed, MNE or Loretta would more accurately capture the broader distribution. Therefore, selecting the right method requires considering whether a sparse or smooth source configuration is more probable, often necessitating additional independent information about the brain's functionality. Welcome to this extended review of AI-powered neuroelectromagnetic source imaging, a transformative framework that leverages the synergy of advanced physics-based models and artificial intelligence to reconstruct the brain's electrical activity from non-invasive EEG and MEG measurements. In this video, we'll explore how this approach overcomes challenges of traditional neuroelectromagnetic imaging techniques, such as noise sensitivity, computational inefficiency, and limited interpretability. Through cutting-edge AI tools, such as convolutional neural networks, CNNs, and physics-informed neural networks, PINs, this method enables highly accurate and scalable, opening new horizons for neuroscience and clinical diagnostics. AI-powered frameworks have transformed this domain, leveraging deep learning approaches like convolutional neural networks, CNNs, to extract meaningful spatiotemporal patterns from high-dimensional EEG/MEG data. These models capture critical relationships in neural activity while overcoming limitations of traditional methods. By employing parameter sharing and sparsity principles, CNNs are computationally efficient and robust to data variations. In addition, advanced model interpretation solutions which enhance the transparency of these methods by uncovering links will be explained. Rather than treating neural decoding as a black box, modern approaches use spatial demixing and autoregressive models to identify the temporal progression and relationships between neural sources. Traditional direct inversion schemes, DIS, rely on physics-based models to solve the source imaging problem. While foundational, these methods face challenges like noise sensitivity and computational demands. Recent innovations, such as physics-informed neural networks, PINs, merge physical modeling with neural domain knowledge directly into the learning process. These hybrid models improve generalization and allow for more accurate source reconstructions. Finally, spatiotemporal neuroelectromagnetic frameworks combine spatial modules for cortical mapping and temporal modules for dynamic brain activity modeling. These AI-driven applications ranging from functional brain mapping to real-time patient monitoring, representing a transformative leap in neuroscience and clinical diagnostics. The applications of this technology span from real-time functional mapping to advanced monitoring and diagnostics in clinical settings. Let us dive deep into each aspect of this work. This comprehensive integration of AI and neuroscience opens new horizons for understanding and decoding the human brain, pushing the boundaries of neuroelectromagnetic source imaging. At the core of neuroelectromagnetic imaging lies the analytical solution of the neuroelectromagnetic problem, structured around two key components, the forward problem path and the inverse problem path. The forward problem is fundamental. It computes how neural currents within the brain generate measurable electromagnetic signals on the scalp. This involves volumetric current reconstruction, mapping the distribution of electrical activity throughout the brain's volume. Impedance inversion, estimating the electrical conductivity of different brain tissues, which is essential for precise modeling. Surface voltage computation, relating internal neural activity to the MEG signals on the scalp. The forward path relies heavily on sophisticated numerical techniques, such as finite element method and finite difference time domain. These tools account for the brain's complex geometry and varying tissue properties. The stiffness matrix, which represents the relationship between and observed potentials, ensures mathematical rigor in these calculations. The inverse problem, on the other hand, reconstructs the underlying neural sources based on measured EEG/MEG data. This is inherently more challenging, as it is an ill-posed problem where small changes in the data can result in vastly different solutions. To tackle this, two primary modeling approaches are employed. These provide a comprehensive map of neural activity across broader brain regions. Dipole models, these offer detailed localization of specific neural sources. At the biophysical level, the inverse path estimates current source densities, while at the physiological level, it models the interactions between neural populations like neural mass models. To ensure accuracy and stability, the optimization framework integrates a data fidelity term, which minimizes the error between modeled and observed signals, and a regularization term, which constrains the solution space. Together, the forward and inverse problem paths form the backbone of neuroimaging, enabling precise and interpretable reconstructions of brain activity. The origins of EEG and MEG signals lie in the synchronous activity of large populations of neurons, particularly pyramidal cells in the cerebral cortex. These neurons generate transmembrane currents during synaptic transmission, producing electric potentials and magnetic fields that propagate through the brain to the scalp. To collect signals effectively, the framework employs convolutional neural networks, CNNs, which excel at extracting spatiotemporal patterns from high-dimensional data. The advantages of CNNs include parameter sharing. Learning shared filters across the input reduces computational complexity, making the approach scalable. This principle captures localized patterns in the data, which are essential for understanding neural activity. Invariance to local translations ensures robustness to small shifts in input data, making the model reliable under varying conditions. The CNN pipeline involves several stages: problem formulation, G/MEG data for neural network processing, data acquisition and pre-processing, cleaning and preparing the data for feature extraction. Feature extraction, using convolutional layers to identify meaningful patterns in the data. Model design and evaluation, designing neural network architectures accuracy and efficiency. By linking decoding outputs to biological mechanisms, CNNs bridge the gap between traditional black box approaches and interpretable models of neural dynamics. The direct inversion method is one of the foundational approaches in neuroelectromagnetic source imaging, offering a direct solution to the inverse problem of reconstructing brain activity from EEG or MEG measurements. This method relies heavily on solving the forward problem, which involves calculating the relationship between neural current source and the resulting electrical potentials or magnetic fields measured on the scalp. The lead field matrix and forward path is computed using precise electromagnetic numerical methods like the finite element method, the method of moments, or the finite difference time domain method. These numerical methods enable accurate modeling of the head tree and the varying electrical properties of its tissues. Software tools such as FieldTrip and Brainstorm are widely employed to solve the forward problem and generate accurate lead field matrices. Once the forward problem is solved, the inverse problem aims to estimate the source currents from the measured signals. Despite its widespread use, the direct inversion method has notable limitations. It is highly sensitive to noise, particularly for sources located deep within the brain. The need for explicit regularization terms adds a layer of complexity, requiring expert intervention to fine-tune parameters for each dataset. Furthermore, the computational burden of solving the inverse problem iteratively can be significant, especially for high-density EEG or MEG systems. These factors can also constrain the spatial resolution of the reconstructed sources, as volume conduction effects and low signal-to-noise ratios limit the method's ability to localize activity. Nevertheless, the direct inversion method remains a cornerstone in neuroelectromagnetic source imaging, laying the groundwork for more advanced techniques such as AI-based frameworks. It continues to be used in numerous applications, including brain-computer interfaces, functional brain mapping, and pre-surgical planning for epilepsy. By combining precise analytical modeling with powerful numerical techniques, the method has paved the way for modern advancements in brain imaging while addressing critical challenges in neuroscience and clinical diagnostics. Interpreting neural activity in the context of EEG/MEG inverse problems requires going beyond black box approaches. Instead of simply decoding outputs, XX, from brain activity as a naive black box, advanced frameworks aim to model the latent source dynamics. Traditional approaches to neuroimaging often treat the reconstruction process as a black box, focusing solely on outputs without interpreting the underlying mechanisms. Modern frameworks, however, aim to uncover the latent source dynamics that drive these signals. Latent sources are modeled using autoregressive dynamics, which capture the temporal progression. The relationship is demonstrated in this slide. To model EEG/MEG data generation, the observed signals are expressed as mixtures of latent sources as shown in the slide, where C is the spatial mixing matrix, and omega accounts for noise. Spatial filters reconstruct these sources, interpretation of the neural dynamics. This gray box approach blends domain knowledge with advanced neural models, enabling the interpretation of how neural signals propagate from their cortical origins to measurable scalp activity. By combining spatial and temporal modeling, these frameworks enhance the understanding of brain dynamics and improve localization. By combining spatial demixing, temporal convolution, and advanced activation functions, this gray box approach enables more transparent and meaningful reconstructions. One of the most advanced AI-powered approaches for neuroelectromagnetic source reconstruction is the spatiotemporal framework, exemplified by methods like DeepSIF. This approach leverages deep learning and synthetic training datasets generated from biophysically inspired neural mass models, offering significant advantages over traditional methods, such as direct inversion or optimization-based techniques. Spatiotemporal AI frameworks bypass the need for explicit regularization by implicitly learning spatial and temporal priors from large-scale synthetic training data. These data, generated by realistic biophysical models, capture the complex dynamic, enabling the deep learning framework to generalize well across different datasets and conditions. By combining spatial modules, such as ResNet blocks for processing EEG/MEG scalp distributions, with temporal modules, such as LSTM layers for capturing temporal dynamics, these methods achieve a higher resolution than conventional techniques. The advantages of spatiotemporal AI frameworks are multifaceted. They demonstrate improved accuracy, overcoming challenges like volume conduction effects and low signal-to-noise ratios, particularly for deeper brain sources. Their robustness across various noise levels and testing scenarios ensures reliable performance in challenging conditions. Furthermore, these methods are computationally efficient, providing rapid inference after training without the need for manual hyperparameter tuning, making them suitable for real-time applications. Their generalization capability allows them to effectively map sensory and cognitive responses or identify regions, such as epileptogenic zones, across diverse patient populations and experimental setups. This novel approach represents a transformative leap in electrophysiological source imaging, addressing long-standing limitations of traditional methods while paving the way for advanced applications in neuroscience research and clinical diagnostics. In this slide, we delve into the improvement of the forward and inverse neuroelectromagnetic problem using a Bayesian perspective, advanced by integrating physics-informed neural networks. This novel approach brings together the predictive power of AI with the theoretical rigor of physics and Bayesian frameworks. The forward and inverse problems on deterministic methods that often struggle with the uncertainties inherent in spatiotemporal neural source imaging. By incorporating Bayesian inference, we explicitly account for these uncertainties, enabling a probabilistic approach to neural source reconstruction. This framework introduces PINN-based inverse mapping, which combines concepts. Information field theory provides a probabilistic framework for modeling and reconstructing spatiotemporal fields, such as neural activity distributions. IFT treats neural source localization as a stochastic process, capturing uncertainties in measurements and modeling assumptions. Information geometry extends Bayesian analysis by exploring the geometric properties of the probabilistic space, allowing for more efficient localization and reconstruction of neural sources. It provides insights into the structure of the source space, enabling the framework to adapt dynamically to varying spatial and temporal resolutions. These tools enable the framework to localize spatiotemporal sources with greater precision and reliability. By embedding domain-specific physical knowledge into the Bayesian perspective, the PINN-based approach ensures that the forward problem generates realistic training data, while the inverse mapping accurately reconstructs neural sources. This combination addresses the challenges of noise, ill-posedness, and complex signal propagation. With this enhanced framework, applications in real-time monitoring, functional brain mapping, and diagnostic imaging are poised to benefit from significantly improved accuracy and robustness. This marks a critical step forward to decode and understand brain activity. This integrated approach represents a significant advancement in neuroelectromagnetic imaging, bridging the gap between physics-based modeling and AI-driven methods, and offering a robust and scalable solution for spatiotemporal source reconstruction. In conclusion, AI-powered neuroelectromagnetic source imaging is revolutionizing our ability to understand and decode the human brain. By addressing the challenges of traditional methods, this framework offers a robust, scalable, and interpretable solution. As we advance, this synergy between physics, neuroscience will undoubtedly unlock new frontiers in brain imaging.